Hi, in this video, we'll be going over Unit 8 of AP Physics 1. So, first, let's establish some definitions for internal structure and density. What is this unit really about? So, what you need to understand is that fluids are collections of molecules and how tightly packed these molecules are determines their density. In turn, this controls how these fluids behave. Which includes buoyancy, pressure, equilibrium, and forces. So, let's start off with the formal definition of a fluid. A fluid is anything that flows. Which is made up of liquids and gases. Something you should know is that fluids cannot resist shear force. And this causes them to change shape easily. Now let's move on to the definition of density. Density is defined using this formula. It's P equals M over V. So, P means density. M is mass. And V is volume. The units for each of these are kgs divided by M3. This is an SI unit that you have to memorize. Mass is measured in kilograms, and volume is measured in meters cubed. So, what are some critical facts about density? Density, let's just write, is an intrinsic property. What does this mean? It means it does not change if you cut the material in half. Also note that liquids have near constant density. Next, note that gases have densities that are variable with pressure and temperature. You need to memorize specifically water and its density, which is 1,000 kilograms over meters cubed, which is equal to 1 gram over centimeters cubed. Also, remember, as an example, ice is less dense than water, which makes it float. So, here are some rearranged forms of this formula that you should try to memorize or to be able to rearrange on the test. Now, let's compare the densities. So, comparing densities, you should know that an object sinks if the density of the object is greater than the density of the fluid. You should also know that the object floats if the density of the object is less than the object of the fluid. Now, you should know that the object is neutrally buoyant when the density of the object is equal to the density of the fluid. Now, let's explain the microscopic definition of density. So, this is up here, so let's bring this down. So, one thing you should know is that mass of particles affects density. So, mass of particle means that heavier atoms means more mass in the same space. And what this means is that this looks a little, the density will increase. Spacing between molecules. So, if there is a tighter packing, then you know that there is more mass per volume. And this will increase density too. Now, finally, for temperature, a higher temperature means that particles will spread, and this will also cause them to speed up. And this will decrease density. What is wrong with this? For gases and often liquids, what is now? A critical thing that you need to remember is the fact that density changes with temperature. And this can also lead to convection currents. It's better if we write it like this. So, to expand on this, because hot fluids expand, this will lead to convection currents. And we know that cold fluids contract. So then you know that it sinks. Let's move this over here a little bit. Now, let's move on to some critical volume relationships. For common shapes. You should memorize these. So oftentimes, density problems involve geometry. And because of this, you know that based off the shape, you should, you should know the volume formula, and you should have these readily accessible in case you need to calculate these. So the volume is, cube is the side, cubed, rectangular, rectangular prism would again just be volume is length width times height. A cylinder would be the volume is pi r squared times height. A sphere would be the volume is 4/3 pi r squared, r cubed. And finally, a cone is volume is 1/3 pi r squared times height. Let's put a line over here. Put that back up. Now, let's move on to linear density, area density, and volume density. So here's the type. Linear would have this symbol, and the formula is equal to m over L measured in kilograms over meter. Now surface area would be this symbol, and this would be equal to m mass over A measured in kilograms over meters squared. And for volume density, we have this symbol, which is equal to m over V, which is kilograms over meters cubed. Now let's move on to the weight of a fluid. So this equation is often used in buoyancy calculations, and it works for the volume of any fluid. Or more so, it works for any volume of fluid. So here is the equation. Mg equals PV times G. Let's box this in like this. Next section is density and compressibility. So you should know that the states of matter liquids, they are slightly compressible. Gases are highly compressible, therefore making the density approximately constant for liquids and dramatic variability. Continuing with Unit 8, let's continue with 8.2, pressure. So, first let's start with what is pressure? Pressure is the force applied perpendicularly over an area. The formula is P equals F over A, where P stands for pressure measured in Pascal, which equals to 1 Newton over m cubed. F is the perpendicular force, and it's measured in newtons. And finally, A is the area over which the force acts, and it is measured in meters squared. Now let's continue with some critical facts. Only the perpendicular force contributes to pressure. Therefore, shear forces do not. Note that smaller area means greater pressure. Same force when under the same force. Also, note that fluids exert pressure in all directions. Now let's continue with hydrostatic pressure. So you need to know this formula. P is equal to PO plus PGH. And basically in this formula, P stands for pressure. P stands for pressure at the fluid's surface, often at atmospheric pressure. The smaller p stands for the density of the fluid, and G is the gravitational constant, 9.8 seconds squared. Let's move this over a little bit. Let's make this A. And H is the depth below the surface. So some critical facts that you should know include pressure increases linearly with depth. Also, pressure depends on depth, not horizontal position. Again, pressure depends on density, not the volume or shape. Of the container. And finally, a weird shaped container gives the same pressure at equal depths. Next, let's move on to gauge pressure versus absolute pressure. So, gauge pressure is pressure relative to atmospheric pressure. And the formula for this is P gauge is equal to PGH. Now, absolute pressure is simply P absolute is equal to PATM plus PGH. Let's move this down a little bit. And let's note for gauge pressure, if pressure at absolute pressure is there. Let's move on to pressure at 2 points. In one fluid. If 2 points have the same depth, they have the same pressure. This is regardless of shape, width, volume, and total amount of fluid. Remember that Pi equals P2 if H1 equals H2. Next, let's move on to pressure in connected fluids. So, if fluids are connected, pressures at the same height are equal. This is used in U-tubes, barometers, and hydraulic systems. Now, let's draw an example of one. Let's say the water flow is going this way. This is H1 and this is the gutter. And the downspout. Let's also imagine another scenario where you have a circle, a spout coming out, and then this shape. And then this is the height of Y. This is the height of X. Let's make this a little more cohesive looking. And then let's fill this up to right here. Now, let's move on to hydraulics and Pascal's principle. So you need to know Pascal's law, which essentially states F1 over A1 is equal to the ratio F2 over A2. And what this law is basically a pressure applied to an enclosed fluid is transmitted undiminished throughout the fluid. And this creates a mechanical advantage. Which is the fact that a small force on a small piston is the same as a large force on a large piston. And you can use it to solve hydraulic problems. Using pressure equality and work consistency. Which states that F1d1 is F2d2. Now let's move on to pressure and force on a surface. So force from a fluid is essentially F equals PA. And these are used in aquarium window problems, dam wall, pressure versus area comparisons. Also, you should know that atmospheric pressure, PATM, is just 1.01 times 10 to the 5 PA. So, let's go back up and review everything. So, basic pressure is P equals to F over A. And what does this mean? It means that more area leads to less pressure. And you use this on any force on surface problem. And then let's move on down here to gauge pressure. So gauge pressure is used on most liquid depth problems. Absolute pressure is used on barometers and scuba. Pressure at depth is the same thing as this. And it means deeper equals more pressure, and the use is for general fluid problems. For gauge pressure, it is pressure due to fluid alone. And for absolute, it includes air above the liquid. And for hydraulic systems, let's see. It is again this Pascal's law. Pressure is transmitted equally. Now, for force on a surface, it is just the total force from a liquid, as we said. And you use this on these three problems. And then, let's see, did we say anything about equal depth pressure? You use this for the U-tube and also for connected fluids. Or action. Let's see here. Pressure at depth. Some more characteristics is that it pushes sideways, upward, and downward.